So the final change we're going to make is thinking about our random surfer model. If this was our model, if a page has no incoming links, well, its popularity ranking would be 0. We don't want to have that be the case. If we think of our random web surfer, well, she randomly starts at a page. She could randomly start at a page that has no links. If we made all the page scores 0 for pages with no links, well, then it would be very hard for a new page to get started. So we don't want those to be 0. So we're going to have some random probability that you reach a page even when it has no links. So that means we're going to add something to this sum so it's not 0 when there are no incoming links. And the other thing we're going to do is we're going to scale this summation a little bit. And we're going to scale that with what is called the damping function. And that just means if we think of our random web surfer again, even if she's following a path that does have more links, at some point she might decide to get tired and give up and start again with a new random page. So the damping function determines how frequently we think our random web surfer will pick a random link versus starting over again on a new random page. So that's called the damping value. And we're just going to use the damping value to scale this number. So we'll call that D. That's the damping constant. A typical value for that is something less than 1. And a good value is something like 0.8. So now we're going to change our rank function to take into account of that. We're going to have some initial value. And if we want to keep the values in a reasonable range, instead of starting from 1, we're going to divide the values by the total number of pages. And the reason for that is just to keep the ranks in some meaningful range. This will keep the ranks, so the total of the ranks when we start, the sum of the ranks is 1. That gives them a little more meaning than if the sum of the ranks was the number of pages. So n is going to be the number of pages, the total number in our corpus, and d is the damping constant. And so now we're going to change our initial values to divide them by n. This means the sum of the page ranks at the beginning will be 1. And we're going to change the way we compute the rank by adding to it a value that that gives us the sense of starting over. So the value that we're going to use for this is 1 minus d divided by n. And that gives the notion that the times when we don't decide to do a new page, so 0.8 of the time we decide to follow a new page. So we're going to multiply this by d. The times when we don't follow a new page, that's 1 minus d, we're going to start over and we're going to divide that by n because n is the number of pages. That's the probability that this is the page that would be picked when we start over. So now we've got our recursive definition of page rank. We start by initializing the rank at time step 0 to 1 divided by n. And then for as many time steps as we want, we're going to keep improving our results by using this formula. For each link that links to us, we're going to take its popularity on the last step, divide that by the number of outlinks, so it's dividing it by the number of other pages that it links to, multiply that by our damping constant. And that gives the probability that this page was selected by the random web surfer. And then we're going to add the term that takes into account the random web surfer might have started over from scratch and picked a new random page. So before we try to change our web search engine to actually program this, it's time for a little quiz. And the quiz is, what is Altavista? And if you don't know this, feel free to use Google or DuckDuckGo to find out. These are the choices. So it's the view from the Udacity headquarters in Palo Alto. It's the most popular web search engine in 1998. It is Spanish for "you're terminated, baby." And it's a small town in Virginia. And feel free to Google the answer if you don't know.